example is probably the most complicated because it actually involves the use of an X or algebra to solve for it. This is the type where you're given just the initial concentration and also the KEQ number, but you are now asked to not solve for the KEQ but the concentrations at equilibrium. So in this question, in a lab, you have 0.5 moles of hydrogen, 0.5 of iodine are placed in a 1 liter flask. The equilibrium constant now, so you have your KEQ, this is at 54.3 at this temperature. Calculate the concentration of HI and HI at equilibrium. So let's write this. H2 plus I2, this is going to give me a reaction of HI. I need to check if this is balanced first because remember the change row, I need stoichiometry. So I have 2 here, and I just need to put that as a 2. So the next thing I'm going to use is going to put this all into ice table and see what I have. So I start off with 0.5 hydrogen, moles of that, but since I have 1 liter flask, that's very convenient because I have 0.5 molarity, 0.5 molar. And then iodine, I have 0.5 molar as well. This is 0 because that's my products at initial, and you notice that that's all that you're given. You don't have anything else, and I can't assume that all my reactants are going to be used up because you don't know that. You don't know if all your reactants will be used up or at equilibrium you have more reactants than products because we haven't calculated that yet. So we can't put 0.5 at equilibrium. However, we can actually have to now put in an algebra or an X. And since that you know that you're going to gain something in your products, you're going to have a plus sign, and because I have 2 for molar coefficient, I'm going to gain 2x. So this x is the unknown that you're going to gain, and the 2 is because you have 2 molar, so that's your 2 times ratio of the other one. And because of this, then we can calculate, or actually just calculate the change for the reacting species, and since this one has a 2 of molar coefficient, all these ones have 1, right? So this is going to be minus x and minus x. So with that, then we can actually just put all this in equilibrium because 0 plus 2x is just plus 2x. This is just going to be 0.5 minus x and 0.5 minus x. So now we have established our equilibrium even though we don't have the numbers. The good thing is that we actually have our KEQ number, right? Because we have KEQ. This is going to be equal to my HI squared divided by H2 times I2. So that's my law of mass action expression. And I'm just going to substitute these numbers in, or algebra. So 2x squared divided by 0.5 minus x times 0.5 minus x. And you can notice that this 0.5 minus x and 0.5 minus x are multiplied to each other, so we can actually put that as 0.5 minus x squared. That's what that is. And the top part is going to be 2x squared as well. I didn't want to do 4x squared because of this reason. KEQ is 54.3. So the reason why I don't want to change all this is that because the numerator is square, the denominator is square, so why not take the square root of both sides to get rid of that? So let's get rid of that. I'm just going to scroll the page down. So what happens is that the square root and the squares will cancel, giving me a 2x divided by 0.5 minus x. And you can probably see where this is going. And the square root of 54.3 is 7.37. So then I need to isolate x, cross multiply this. So 7.37 times 0.5 minus x is equal to 2x. Okay, so far so good. Distribute this, so 7.37 times 0.5 is equal to 3.68 minus, this is multiplied by x, so I get 7.37x is equal to 2x. I'm not done yet because I need to isolate x, and since I have x here and x here, I need to move them onto one side, so I add 7.37x to both sides just to get rid of it from the left side. This will cancel. 3.68 is equal to 9.37x. And you can see that the last step is coming up pretty soon because we just need to divide by 9.37, 9.37, which cancel this all out, is leaving me with x, and that number on the left is 0.39. And this is x, and how we calculate for the concentration is that now we have to look back up. What does x represent? Well, HI is 2x, so we can actually calculate what 2HI or HI is. Whoop, HI. HI is 2x, so then 2 times 0.39 is 7.8. 0.78. What am I talking about? 0.78. That's the concentration of my HI. And my H2 and I2, this is where they had 0.500 minus x, which is 0.500 minus 0.39. This will give me an answer of 0.11 molarity. So this is for the concentration of H2 at equilibrium. This is going to be the concentration of I2 at equilibrium. So just to recap, if you got a little bit lost here, this one you're asked to find the concentrations instead of KEQ. You're only given the initial amounts, and because of that reason we need to just put an algebra in there, an x, and we put that into the change row because that's what you're gaining in the products. And why I have this too, because of the molar coefficient, and these two reactants have just one, so instead of having 2 I have 1. So I gain, so I have positive, I have minus for the reactants because I'm losing. And then once I have that, I can establish my equilibrium row because this is just going to be plus 2x. This is my 0.5, what I started off with, minus what I used up to make the product, which is x. Bam. And then once I have the equilibrium row, I'm going to put this into my law of mass action expression. And I have this, 2x squared, and then the bottom number, this is usually going to be square. If we're not, there is an example where you actually do have to use quadratic, but this one doesn't. And then take the square root and then solve for x. Once you solve for x, you just substitute this x number back into your original amount, which is 2x. So your HI is 0.78 molar. H2 and I2, they're 0.11 molar. So this is the most difficult one out of all your ice chart calculations. But practice it. You can stop and replay this. Hopefully this video has helped you calculate this. So thanks for watching.